at the University of Houston, where he was a physics and math major. He then transitioned to the University of, or UC San Diego, started as physics, but then transitioned from there into oceanography at Scripps. So he got his PhD from Scripps. That was in 2004. From there, he started a postdoc at Caltech and was working affiliated with JPL. He started officially as a scientist at JPL in 2006, and since then has been working on all sorts of things related to sea level rise. He's been the project scientist for a lot of the JASON missions, which you may know are the satellites that measure our sea level. He's also done a lot of work on the Argo program, which is the other component of sea level. And I've had the pleasure to work with Josh, both when I was a graduate student and then also when I was a postdoc at JPL. So without further ado, we can welcome Josh and yeah.
Cool. Thanks so much, Mike. I really appreciate you having me. I'm unmuted, right? You can hear me?
Yeah, you're all good.
Rock and roll. Thank you. Save me a slice of that pizza, okay? It looks good. Um, thanks again for inviting me to do this talk. It's a real pleasure and an honor to get to talk to so many interested and motivated folks. Um, yeah, I'm going to tell you a little bit about just the science that I do and some other stuff too. I'm a scientist and have been for over 20 years now, but I'm also a science communicator and an artist in my spare time. So I'll give you a little bit of a flavor for all of that stuff. I personally have always felt that as a scientist, we have a responsibility to help communicate what we're doing to the public. Almost all of our research is funded publicly, and so I think it's important for us to tell the world what we're doing, and that's especially true, I think, today with climate science, which is really what I got my PhD in. Mike said I transitioned from physics to oceanography, which is a funny way to put it. Actually, I failed out of physics, and oceanography let me stay. But it came to be really a really great passion for me. Part of the reason I struggled with physics was because I didn't find a connection to a topic there the way I did with studying the ocean, and in particular studying the ocean and its role in climate. And so that's what I'm going to talk a little bit about today is the ocean, its role in climate, and my role in studying it, and sometimes talking about it. So just to start with, this is a picture of me. Hopefully you can all see my slides. This is a picture of me at the launch of Sentinel-6 Michael Freilich. That's the satellite that I work on at JPL. It's a satellite that measures sea level from space, and measuring the rise of the oceans has been a central part of my career, really since I started at Scripps. So it's very near and dear to my heart, as is that NASA sweatshirt, which I refuse to give up, even though it's kind of beat up and dirty now. So climate change and the art of science. I think as scientists we have to find a way to express ourselves, and you'll hear a little bit about how I do that as well. Speaking of expressing myself, I just want to show you this video really quick. I started working on these missions that measure sea level a long time ago, and in 2016 we launched JASON-3, which was a successor to JASON-2, JASON-1, TOPEX Poseidon. We'll talk more about those later. But this was the first NASA mission that was launched on a SpaceX rocket. And if you were following SpaceX back in the day, this was back when they were still trying to land the rocket on the barge. They hadn't done it successfully yet. And so the reporters who were at the press conference for this launch were very excited about the rocket. And one of them asked me about it. And so this is a true story. This is what actually happened at that press conference.
We'll take questions now, and we'll start right here in the front.
Can or will you guys care to comment on the launch vehicle?
I will say that we're excited to get a ride to space, and we hope SpaceX breaks a leg.
Yeah, I don't know if you could see in that video, the leg broke on the rocket and it fell over. I actually showed that video at SpaceX. I went there a couple years ago when we were about to launch another sea level mission with them, and I showed that video, and people kind of laughed. And at the end of my talk, a guy came up to me afterwards, and he said, "I know about you and your video. I'm the engineer who had to work on that leg and sift through all the rubble on the barge in the jet fuel and try and figure out why it broke." And I was just silent. And he said, but I liked the video. It was very funny. So big relief. But yeah, as you can see, I kind of like to get in trouble and put my foot in my mouth, which I think is part of being a scientist too, as you'll find out more later on. So what is it that I do? Well, I study the warming of the planet in the broadest sense. I think we all know the planet's warming up. The temperature of the Earth is rising. This is a measure of the temperature, really, of the surface of the Earth. And it's been rising for the last 100+ years. Um, the reason is not a mystery. We know it's because of increasing levels of carbon dioxide in the atmosphere. And we know this really because we can look back in time, drilling down through glaciers and ice sheets and measuring past atmospheres. When snow falls in these places, and if it doesn't completely melt during the summer, then it traps a little bit of air. And by measuring the composition of that air, we can figure out how much CO2 was in the atmosphere back then. And by measuring different isotopes, we can actually tell the temperature of when that snowfall fell as well. So we can measure the temperature and composition of the atmosphere going back hundreds of thousands or even millions of years. So, how does global warming work? I'm sure every one of you has seen some version of this slide before. This is my version. But basically, light from the sun comes through the atmosphere. The sunlight is the atmosphere is transparent to sunlight. So sunlight comes in, goes right through the atmosphere. Maybe a little bit bounces off clouds and shiny surfaces, but by and large, most of the sunlight goes to the atmosphere and it warms the surface. That warm surface tries to radiate heat back out to space, but the radiation going back out is not sunlight anymore. It's in the form of infrared radiation. And that infrared radiation is very sensitive to what's in the atmosphere. So as we add extra CO2 and other greenhouse gases to the atmosphere, some of the outgoing heat gets trapped. And so the question is, where does that heat go? And the answer is probably one you've heard of at this point in your own science career. Over 90% of the heat that's trapped by those greenhouse gases is actually warming the oceans. So we think of climate change and global warming as something that's happening to the air. And of course, that's true. But really, climate change and global warming at the 90% level, they're happening in the ocean. Um, the ocean absorbs all this heat. It absorbs about a third or a quarter of the carbon dioxide that we put in the atmosphere today. And it's really the definitive measure of how we're changing the climate, how much heat's going in the ocean. Of course, the warming atmosphere also melts ice. This is a picture of a glacier in Alaska. This is a famous pair now. But in 1941, the glacier extended all the way down this long fjord, and then someone went back to the exact same spot, took the exact same photo in 2004, and you can see that the glacier has retreated many miles up into this canyon. And glaciers are retreating around the world. Over 90% of all the glaciers in the world are in retreat as the planet warms up. So as the glaciers melt, they add extra water to the ocean, and this causes sea levels to rise. Sea levels have been rising like this for the last 150 or so years, a couple hundred years, since the Industrial Revolution. And it's interesting, we actually have, you might have heard of the hockey stick, which is where they try and reconstruct temperatures before the 1800s with tree rings and other things, and then merge those temperatures with instrumental records, which started really at the beginning of the Industrial Revolution. And it's a little difficult to do, but in sea level, we have our own hockey stick, and it comes from looking at sea level in these salt marshes. This is a record taken from a beach in North Carolina, and this beach is actually slowly rising due to the end of the last ice age. The continents are shifting and moving a little bit from the end of the last ice age when there was a giant ice sheet on top of North America. So this coastline is lifting up, and as it does, there's a very narrow tidal range here. So the tides don't change very much between high and low tide. And there's an assortment of little critters that live in very narrow ranges of the tidal range. So you can drill a hole down through the mud and measure the critters, what kind of critters there were in different times at different depths. And you can do this in a bunch of different places, and you can actually reconstruct the rate of sea level rise over the last 2,000 years. And basically, for 2,000 years, most of 2,000 years, sea level didn't rise at all. It was very steady. There was a little bit of rise at the end of the medieval warm period, maybe a little cooling during the Little Ice Age. And then when the Industrial Revolution happened, then sea levels began to rise very rapidly. And on top of this is a blue curve where we have actually a tide gauge in almost the same location. So we have these really amazing records looking back in time. If you're kind of a detective, this is sort of a fun mystery story to try and go and solve. They all point to essentially the same conclusion that the warming of the last 150 years is very out of the ordinary, and it's driven by the changes we've caused in the Earth's atmosphere. So just to bring us to a little more modern times, so this is where I come in. These missions are all missions that measure sea level from space. So we have these salt marshes telling us 1,000 years of sea level change. We have tide gauges, which tell us the sea level change in one location somewhere along the coast, and some of those have 100 or 150 year long records. But in the modern era, we have satellites. And these satellites, starting with Topex Poseidon launched in the early 90s, that's the satellite that actually got me my PhD. And after that, it was followed by Jason 1, Jason 2, Jason 3, and then now actually there's Sentinel 6, the name change. It's not Jason CS anymore, it's Sentinel 6. And there's two of them, a Sentinel 6A and a Sentinel 6B, launched 5 years apart, and measuring sea level along a very tightly controlled track, so that we can really look at how the sea level is changing over time. And the way these satellites work is they fly around the planet, bouncing a radar wave off the surface. The radar wave takes some time to go down through the atmosphere, bounce off the ocean, and come back. And by measuring that time very accurately, we can tell how far away the water is from the satellite. Then there's positioning systems that tell us where the satellite is in space. You have the position of the satellite, you have the distance to the ocean. You can subtract those things and you can tell the height of the ocean. And there's other instruments that help us do this more accurately and so forth. But by measuring the height of the ocean all over the planet, we can get a snapshot once every 10 days, which is the repeat cycle of these satellites, which shows us how sea level is changing really everywhere across the globe. And it's revealed some really fantastic things. We can see things like El Nino in the Central Pacific. This is data collected during one of the biggest El Ninos of the last 30 years. You can see the red means sea level is high along the equator in the eastern Pacific Ocean. That's indicative of warmer waters there. When the water is warmer, it literally expands and stands taller. And this rearranges the atmospheric circulation and the rainfall in the Pacific Ocean, and actually shifts weather patterns all across the globe. In El Nino years here in Southern California, we tend to get wetter winters. In Northern California, Oregon, and Washington, they tend to get drier winters during El Nino years. It's not a perfect correlation, but it's usually a pretty good indicator. So El Niños come and go over the course of a year or so, and these satellites give us this global picture of El Niño. And it's the first time we've really been able to see the extent to which this climate pattern really affects weather all across the globe. So, what does sea level look like? Play this little animation too. This is sea level not just from one single satellite, but satellites. There's more than just those few that I talked about, and they fill in some of the gaps. We can see smaller changes. A lot of what you're seeing are eddies. If you look carefully, you can see the seasonal cycle with the southern hemisphere getting warmer and then colder and then warmer, and the northern hemisphere changing in an opposite way. So there's all kinds of stuff we can measure about the sea level from space, and it really gives us this amazing bird's eye view of how the oceans are changing in a way that we never had before these satellites. Now, of course, if you average the sea level all across the globe, you can see things like global sea level rise. So if we look at how the average of those have changed over the years, this is a plot of that starting in 1993, and then adding each year on top all the way till we get to, I think this ends in 2024. There we go. And if you put them all together into a time series, it looks like that. Now, if you remember that plot that I showed at the very beginning of the temperature rising over time, there were all these jumps and ups and downs. There was a long-term rise. But really what we see here is a very clear indicator of the fact that the global sea levels are rising quite quickly and quite clearly. In fact, this record is very, 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 very smooth and very, very clear. It's so accurate that we can actually see every year there's a rise and fall in the global oceans. This has to do with the atmosphere evaporating water out of the oceans. It falls as rainfall over land. And it takes some amount of time for that rainfall to run back into the ocean. And during the time that the rain is sort of sequestered on land, the sea levels actually drop. So this rise and fall that you see that happens every year is the movement of water back and forth between the oceans and land. So you can think of this like the heartbeat of the planet. It's really a bird's eye view of the circulatory system of our planet, moving the water from the ocean through the atmosphere to the land and back again. But what's clear is that that's a natural signal having to do with the seasons. But there's this other signal on top of it that's the long-term rise in global sea level. You can't really see it on this plot. I'll show you another view of it here. It's not really a straight line anymore. A straight line doesn't fit very well, this global sea level rise. In fact, you have to draw sort of a parabola through it to fit very well. And the data tells us that in the early 90s, sea level was rising at a rate of about 2 millimeters per year. In the 2000s, it was more like 3 millimeters per year. And now it's close to 4.5 millimeters per year. So the rate of rise has more than doubled in the last 30 years. And this is the clearest feature in this data, right? You can see the rise and fall of the seasons, but the total amount of rise that we've caused because of climate change is actually 10 times bigger now than this natural cycle of the rise and fall of sea level. So the satellites are telling us something very profound about how the global climate is changing, but that's not really why we started flying them. We started flying them because changes in sea level also tell us about ocean currents. When there's a high sea level and a low sea level, it tends to mean that there is a current going in between the high and the low. In the northern hemisphere, the high sea level tends to be on the right and the low sea level tends to be on the left. And this would mean the currents going in between them. And this happens because of the physics of the ocean. Whenever a large body of water is moving across the planet and it continues to move for more than just a day or two, the rotation of the Earth starts to become important in its movement. And this rotation winds up balancing with a pressure force. So you can imagine the sea level's high over here and it's low over there. That means the water would normally try to run downhill just from the force of gravity. But in the oceans, we see these slopes in the sea level that have to do with the fact that the water's moving. So the high and low is actually balanced by what's called the Coriolis force, which is a force that the water feels when it's moving because the Earth is also rotating. So if we look at the sea levels all across the planet, and just the part that's related to ocean currents, we get this really amazing picture of how the ocean currents change. And if you look here, then the places where the lines are close together, we have a very steep gradient or a steep slope. This means that the water is moving very fast. And if you know a little bit of oceanography, you might have heard of the Gulf Stream, which is the big current that runs from south to north along the United States east coast. This boundary current, it's called, carries a huge amount of water from the southern tip of Florida off the coast of the United States and through the North Atlantic, and then eventually makes a little circle around Greenland and comes back down. There's a similar current in the Pacific called the Kuroshio and Kuroshio extension, and we can really see where all these currents are in part because we have these satellites measuring sea level. Now, I mentioned this before, but whenever water is warmed up, you have this phenomenon where the water literally expands. So just like a metal, if you have mercury in a thermometer, right? When you heat up the mercury expands, it moves up the thermometer. That's how the thermometer works. Seawater works the same way. The effect is small, but because the ocean is thousands of meters deep, when you add up the effect over those thousands of meters, you can get centimeters of sea level change, many centimeters, sometimes even a meter of sea level change, just due to the fact that one area of water is warmer than another area of water. And that means that the high sea levels also tell us where the water is warm. And it tells us where the water is warm, not just at the surface, but over depth. And this is important for predicting things like hurricanes and where hurricanes are going to speed up. Hurricanes are these giant storms, but they get their fuel, their energy from the warm water over the ocean. As they sort of suck warm water out of the ocean, the winds mix that water from the surface down to deeper layers. Now, if those deeper layers are cold, then when you mix the water, the surface cools quite a lot. But if the deeper layers are warm, when you mix the water, then the surface doesn't cool as much. And that can cause the hurricane to speed up very rapidly. And in fact, most of the hurricanes that have sped up very rapidly have done so in recent years because they've crossed a place where we have very high sea level, which means very warm water, not just at the surface, but over a range of depths. This is a track from Hurricane Katrina, which very famously struck the coast of New Orleans. And you can see this big blob of warm water, which the hurricane encountered just before it went ashore. And so it sped up from a category 3, I think, to a category 5 before it made landfall, mainly because of this big patch of warm water that was sitting there in the Gulf. So these satellites also help us predict how hurricanes speed up and how they're changing as well. So they're important for weather forecasting too. So now I'm going to shift gears a little bit and tell you about a different satellite. I work on the satellites that measure sea level, but there's also these really cool satellites called the GRACE satellites, or GRACE follow-on satellites now. The GRACE satellites are actually a pair, and they chase each other around the planet. So whenever the first one flies over something heavy, like a mountain, then the pull of gravity literally causes the satellite to speed up and move away from the one chasing it. So you can see that in this illustration here. The first one will come upon a mountain. the pull of gravity causes it to speed up. When the mountain's between them, the pull of gravity pulls the two together, and then they re-equilibrate when they pass over the mountain. So by measuring the distance between these two satellites very, very accurately, you can actually weigh the continents. You can weigh Greenland. And when we weigh Greenland, we find out that Greenland has been losing a whole lot of water. Oh, but I realize I disorganized my slides. Hang on one second. I'm going to come back. I'm going to come back to this in just a second. Okay, here we go. Here's Greenland losing mass. Um, uh, so this is Greenland losing mass as measured by these GRACE satellites. And you can see as the edges turn red, these are the locations where Greenland is losing mass. Now, these satellites fly at an altitude of about 400 kilometers, which means that they can't see very fine details. They kind of smear out the signal over several hundred kilometers. But you can see that around the edges of Greenland, these are the places where the ice is disappearing the fastest. And that'll become later, that'll become important later when we talk about things like OMG. But before we talk about that, I'm going to back up here. I got my PhD by studying ocean warming. I mentioned I used data from the Topex Poseidon missions. But when I was studying to get my PhD, I calculated the amount of warming in the oceans using a combination of measurements of the temperature along with measurements of the sea level. And so I made this really great, very accurate estimate of how fast the oceans were warming. So then I graduated and I went to JPL, and a couple years later it became time to update the estimate of ocean warming. And some colleagues and I were working on it together, and so we updated the estimate of ocean warming, but it actually looked like this. So the blue part is what I did in my PhD, and then the red part was what we calculated after I graduated. And you could see all of a sudden the oceans were cooling. And this really freaked us out. We didn't know quite what to do. And we looked at the data very hard and we tried to understand what the cooling came from. But in the end, we couldn't actually find anything wrong with the data. So we published it. And when we published it, it started to gain attention from sort of the wrong crowd, you might imagine. And I don't know, you're probably all too young to know who this guy is. But Rush Limbaugh was a radio host around this time. And he had a guy on his radio show who called in and told him about our ocean cooling result. And this is, basically, we didn't really understand why it happened. And this is what Rush Limbaugh said.
To overturn the world economy based on the musings of a few idiot leftist scientists is just stupid, and that's what global warming is actually all about.
Yes. So there's me, stupid. Right? So this actually happened to me, and it was sort of an important moment for me in my career because it was, exactly the wrong kind of attention from exactly the wrong guy that you don't want to have attention from. And I had been giving lectures on this ocean cooling for quite a while. And so when after this happened, I was actually about to take my wife on a date for Valentine's Day. We were about to go out, and the following week I had to give another lecture on ocean cooling. But before we were going out, I just made a couple of quick calculations, and I figured out that there was a problem with some of the data that went into that ocean cooling estimate. And I said, uh-oh, I think ocean cooling might be wrong. And we still, the Valentine's Day date was totally ruined because I was thinking about this the whole time. But she eventually forgave me and made me business cards that said idiot leftist scientist. Which if I was there, I would hand out. But what we eventually figured out was that there was a problem with some of the data that went into the estimate. Some very specific, very small, very difficult to detect biases. And when we eliminated those, eventually we were able to recalculate ocean warming, and didn't drop anymore like that. So that drop would have been somewhere in here, or actually somewhere in here. The thermal expansion of the warming part of the ocean sea level change that we calculated went away. And I tell this story not just because I think it's funny and to shame myself, but because I think it's important to remember that as scientists, sometimes we make 3 steps forward and 2 steps back. And honestly, if we're really pushing ourselves to try and learn new things and make new discoveries, then we're going to have those moments in our careers. So after we figured this out, I published a correction to ocean cooling, and I went around and gave lectures to everybody about how I had messed up and we had to fix it. So this was another point in my career where I felt like it was really important to sort of tell the story of what happened. And I bring it up because as young future scientists yourselves, hopefully, when things like this happen to you in your career, the important thing is to not be discouraged, to be open and honest about it, and to realize that it's part of the process of doing science. It's not always a everybody moving in the same direction at the same time kind of thing. So anyway, you can ask me more questions about that at the end if you want. We talked about this one already. Oops. Okay. The ice is melting. We realize the ice is melting from the warming planet. This is just a nice little video that I took of a glacier in Greenland that was actively melting during the summer. Mike came with me on this trip. I think you were there for this one, or one like it. But as we've started to look at Greenland more carefully, and based on that image I showed you from the GRACE satellites, scientists began to realize, and it wasn't just me, it was before me, but we began to realize that the edges of Greenland were melting faster. And the thing that's unique about Greenland is that the glaciers there are connected to the oceans. And so we wanted to explore that connection. And in order to do that, we proposed a which wound up being 6-year-long mission to fly airplanes around Greenland and measure the oceans and the ice and try and understand how much the oceans were eating away at Greenland's ice from below. So I'm just going to play a really quick video just to give you a sense of this mission.
There's enough ice here in Greenland to raise sea levels by 25 feet all the way around the world. It's an incredible amount of ice, and it's melting and adding to sea level rise. For oceans melting Greenland, what we really want to do is measure the oceans, measure the ice, and watch them change together year on year, and try and answer the question, how much are the oceans melting away the ice, as opposed to the air, which is what most people have studied so far. It's really a breathtaking landscape. These giant mountains and canyons are all along the coast. When you look out the window, you really get a sense of just how huge these glaciers are, these gigantic rivers of ice that are draining the ice out of Greenland into the ocean. And then they reach the ocean and it gets all broken and craggy and big chunks fall off. It's incredibly dramatic. Kulisuk is just a tiny little town in southeast Greenland, and we've been launching probes out of here for the past 4 or 5 days. It's already been a fantastic year for OMG measuring the oceans. We launch them right out of this tube right over here. Open up the tube, you can look right down it and see the water passing by, or sometimes the icebergs or clouds or whatever it is we're flying over. We slow down a little bit and we just push these big gray cylinders out of the bottom of the plane, and they fall to the ocean and measure the temperature and salinity when they get there and radio it back to the plane. we're really trying to look at the ice and ocean all the way around Greenland. So we're dropping 250 profilers. We're going to cover the coastline all the way around. And in the spring, we map out the glaciers with a radar, also all the way around. So we're really looking at mapping all of the ocean-ice interactions in Greenland as best we can with one mission.
That's a little bit about OMG, and which we did in part during the pandemic. There's your fearless leader there, well, this guy's Finty, Mike Wood. Thanks again for having me, Mike. And these are just some fun pictures. But to give you a sense of why we really needed to do this in Greenland, oops, wow, I hit the wrong button. Okay, here we go. Why we needed to do this in Greenland. This is an animation showing what a typical glacier in Greenland kind of looks like. It's this long river of ice, and in the summer, the melt at the surface collects in pools, and these pools can actually drill a hole all the way down through the ice and carry meltwater to the bottom of the glacier. Now, this meltwater runs along the ground, along the bed below the glacier. It's completely fresh, and when it reaches the seawater, an interesting thing happens. The seawater is salty, and so it's always heavier than this fresh meltwater. And the meltwater, when it reaches the bottom of the glacier, it starts to rise. And it rises and it actually pulls in this layer of warm, salty water. And that warm, salty water eats away at the bottom of the glacier. After this happens long enough, a big chunk of the glacier can break off. And then this can cause, ultimately, if a lot of that happens, then this can cause the glacier to retreat. And as the glacier retreats, the glacier winds up speeding up and dumping more ice in the ocean more quickly. And just as a reminder here, I'm going to back up in this, if I can find it. Sorry, bear with me. There we go. The water around Greenland is what I call upside down. So we have this layer of cold, fresh water that sits on the surface. That water is from the Arctic. It's the freshest. It's all cold. All the water is pretty cold there, but the freshest water in the oceans comes from the Arctic because it's partly covered with sea ice, so there's not much evaporation. There's lots of runoff into the Arctic from rivers in Siberia and northern Canada. And so it's very fresh. It's a very fresh ocean. In contrast, the water from the south, from the Atlantic Ocean, is the saltiest water of any ocean. So you have this very salty water that's underneath, that's from the south, and this very fresh water that's from the north. So the salinity winds up mattering more for which one's heavier. So this warm, salty water is actually heavier than the cold, fresh water, and it sits in a layer below. So this is one of the reasons why we had to actually go to Greenland to measure the water there, because you can't measure this warm, salty water using some kind of radar or anything at the surface. You really have to put a thermometer down there in the deep water and measure how warm that water is and see how it's changing over time. And that was the idea behind OMG. This is just another cool picture of an iceberg with a chunk that fell off and calved. Lots of cool photos and videos there. I'll give you a web page you can check out and see more at the end. But our plan was to fly airplanes around and use sensors to measure this deep warm water that we dropped out of the plane. These were one-time use sensors. They're expendable. The X in AXCTD stands for expendable. And they collect one profile, radio the data back to the airplane in real time, and then that's it. Then they eventually sink to be discovered later by angry fishermen. So we also flew airplanes over the ice with a radar to measure how the ice was thinning or retreating. And together, these two pieces of information really gave us the tools to understand how the oceans were eating away at the ice from below. This is just another cool picture, another cool video. It's a time lapse. We didn't really fly this fast, but we were able to fly and then drop sensors in places as small as that little, that tiny little spot right there. I don't know if you can see my cursor, but right there, that's a little hole in the water, a little open hole in the water. And these pilots were so good they could fly us over and we could drop sensors right in things that small. So we did this. We collected a lot of data in different years, different kinds of data, ocean data, ice data. Um, we flew by giant icebergs that were so big they blotted out the sun, like this one. Yeah, I think Mike was actually in the plane for this one too. That spire was so tall it cast a shadow on the plane. Um, and what we found out was that the oceans play a huge role in melting the ice. I won't go through this in too much detail. There was a big glacier there that actually demonstrated this relationship really clearly. But Mike actually wrote the sort of seminal paper for this mission, Oceans Melting Greenland, or OMG for short, looking at all the glaciers all the way around Greenland using data that we collected, both temperature and ice data. And he found that in times where the ocean was warming, the ice loss around Greenland was faster. And in times where the ocean wasn't warming as fast or even cooled just a little bit, this is part of a natural cycle superimposed on a longer term warming trend. During the cooler periods, the ice loss slowed. So we demonstrated that there's this really strong relationship between the water temperature around Greenland and the ice there. And that's important because if you want to predict what's going to happen to the ice in the future, it means that you have to keep measuring the ocean temperatures around Greenland in order to do that. It's not just enough to measure what the atmosphere is doing. You really have to measure the oceans too. Some more cool pictures. This is another plume. So sometimes when that water from the runoff rises up the face of the glacier, it rises all the way to the top and it actually pushes this free-floating ice away from the glacier edge. Here's another plume. This is another time we flew very close to the glacier. You can see the shadow of the plane on the glacier. Uh, that one I was hanging on for dear life. But it was a very interesting, and exciting mission to fly around and do this stuff. Let's skip over a few of these other cool pictures and talk for just a second. So at the very end of OMG, we decided to try and start dropping sensors that would not just give us a single profile, but would last for a long time and keep collecting more and more profiles and send data back to us instead of through the plane, through the Iridium satellite communications network. And this is one of those. Floats. We were lucky to be able to deploy a few during OMG, and you can see that you have the OMG mission where we collected data once a year for some of these places like this, and then when we dropped a float, it would collect a whole time series of temperature data, so you could really see in much greater detail how much the water temperatures down here were changing. And very excited to have this guy still going to Greenland from time to time. This one was from a couple years ago, but still deploying more of these floats around Greenland. There's Mike and our buddy Lorenz, who works in Greenland, and we deployed this float in this really beautiful, amazing fjord. And it lasted quite a while and provided us a lot of really interesting data from the fjord. So we're continuing to, with programs like this, we're continuing to try and measure these water temperatures and how they're changing over time in hopes that we can better predict what the future of Greenland ice looks like. So if you want to learn more about this, you can go to omg.jpl.nasa.gov, read about the mission. The mission's concluded. We finished up in 2021. But as I said, Mike and some other people that are almost as cool as Mike are still deploying floats there in Greenland and collecting really important data. So I'll just leave you with one last thing. I talked at the beginning about how important I thought it was for us to communicate about what we're doing as scientists. And I had a really unique opportunity to communicate about my science. A few years back, there was this contest where scientists were asked to make a video answering a question asked by an 11-year-old. And that year, the question was, what is climate? So I made this video in response to that answer, and I'll just leave you with this.
Hello there, little lady.
Say, what's climate?
Well, you curious little ankle biter. Climate is the...
What?
Let me try something a little different.
Sunny on Sunday, high 73. Monday, rain was pouring down on me. Tuesday was cold, I almost froze my toes. Oh, what's it gonna be next week? Who knows? That's weather. Oh, that's the weather you got. But you take a bunch of weather and you average it together and you're doing the climate rock. A climate is the average of the weather you see. The critters and plants all know where to be. A cactus can't live in the tropical rain, and polar bears don't dig by rain. That's climate.
Wait a minute. So, are you saying that plants and animals know about climate too?
Well, that's right, little Miss Jane Goodall. Every living thing on Earth is adapted to the very specific climate that it lives in.
Wow, that's wild.
That's not just wild. Well,
That's climate. Oh, that's the climate you got. Maybe. You take a bunch of weather and you average it together and you're doing the climate rock.
So there you go. I'll just put these on, and you're welcome to ask any questions. If you want to see the rest of that video, you can Google Climate Elvis. Thanks again for having me. The best part of showing that was seeing all the faces in the front row get covered and go like this during the start of the video. That was my favorite part. Yeah. So that's a little bit about me and my science journey, as it were. Feel free to ask me about any of it. Happy to talk.
All right. Thanks, Josh. That's the end, right? All right, so normally we have a microphone that we pass around, but today I guess we're switching the technology up and we have the owl. So if you have a question for Josh, it might be helpful if you come close-ish to the owl to ask a question.
Yeah.
Don't be
Or
shy.
a question for Climate Elvis. Just be
Or
sure you
Climate
know who you're
Elvis,
asking.
yeah. Climate Elvis also has all of the handles, Instagram and all those if you're
Right.
interested. But yeah, questions for Josh? Yeah, come on.
You see me okay in there?
I can't see you, but I can hear you.
Okay, I'll
Go
sit
for
next
it.
So I'm curious about when you realized you made your mistake about the cooling, and what was like the next step that you took from there? Like, how did you, like, I'm imagining you like at your laptop being like, oh my God. And then like, what's next, you know?
Well, I took my wife to dinner that night, and but I actually wrote a colleague an email, and he wrote back really quickly, and so the data that we were using to do that calculation was a combination of an older type of data that were collected on ships, which were similar to the expendable probes that we used in Greenland that we launched from planes. So these expendable probes had been used for decades. And we thought we had them pretty well calibrated and understood. And then in the early 2000s, we started using a new type of data from Argo floats. And these are similar to the floats that you saw at the end that we deployed out of the airplane. So it turned out that it was sort of a combination of switching from the old data set to the new one. The old data set had a warm bias that we hadn't completely eliminated. And then in the new data set, in the Argo data, it turned out that there were a small number of floats that were malfunctioning, and they were recording temperatures correctly, but they were labeling them at the wrong depths. And so this wound up, actually, they were labeling them too shallow. So it wound up taking cold water and moving it to a more shallow position in the temperature profiles. So when we combine these data sets, it made it appear that the ocean was cooling. So it took a little while for us to completely unravel what was going on. But once I identified this set of floats, and I used my colleague at Scripps, who was involved in the development of Argo, to help identify them. Once we eliminated all the bad floats, that cooling went away. And then a more careful look at the differences between the old data set and the new data set yielded this bias between the old expendable probes and the new well-calibrated Argo data. I say well-calibrated except for those ones that were malfunctioning. So in the short answer to your question is we went to work. Me and a bunch of other colleagues started really dissecting the data and really trying to identify and eliminate these biases. But the other thing I did was I literally went on a speaking tour, and I went around to kind of all the places where I'd given talks about ocean cooling, and I gave talks about how the cooling was incorrect and that there were these two data biases that we had to figure out how to deal with as a community. So my approach was with it was to be very upfront about it, to talk about it, and then to try and help identify and correct the problem that caused it in the first place, because it was one that we were definitely going to have to fix eventually. So in a way, it stimulated a lot of new work, and I think the real answer to your question is that I just dove into that work and worked really hard to find a new answer. So, in a lot of ways, mistakes help you hone in on new important questions, and I think to me that was really the lesson as a scientist.
Thank you so much.
Thanks for the question.
Yeah.
So my question was also about that story, but I was curious if you engaged with the Rush Limbaugh crowd or how you dealt with it.
Yeah, I mean, well, sure. I mean, I tried to talk to. I've tried to talk and be open to, the all media and all sides. Sides, I guess that's a loaded phrase in and of itself. But yeah, I tried for a long time to connect with people who had firmly held beliefs that science was fake. And in my experience, actually, it helps, at least on an individual level. I can remember there was an email, for a while I was getting nasty emails from people telling me I was faking the data. And I got one, and I decided it was from some, dentist in Iowa or something. But he wrote me a really nasty email saying I was a huge liar and that I should stop faking the data. And I wrote back to him and I said, look, I've spent my career doing this. I know hundreds of people who've spent decades studying this data. And, the evidence is real. I mean, these people they're real people and they have real lives, and they're really studying this stuff and dedicating their entire, careers to understanding climate change. And everything points to the fact that it's real. And it was interesting because the guy wrote back to me and seemed surprised to find out that I was a real person. And that I wasn't just like some machine spitting out propaganda. So that little connection that I made, that little personal connection, helped. The problem is it's very hard to do that on a large scale. I can talk to the one dentist from Iowa, but I can't talk to the millions of folks who listen to Rush Limbaugh all at once. So it's a conundrum. But personally, I think the right answer is to stay as engaged as possible and be as clear and honest as possible. As scientists, I think it's also very helpful for us to own our mistakes. When I put my foot in my mouth, I make a video about it, right? And I share it and I'm honest about it. And I think that's important to help us maintain. I don't want to say maintain our credibility. Our credibility has been under attack, right? And so it's taken a hit in some places. So we have to rebuild it. And I think one way is being honest about when we trip up.
Any other questions for Josh?
Yeah, I'm the oldest guy in the room here.
Oh, great. Awesome.
Yeah, graduated Moss Landing Marine Lab, original lab back in the 70s. And a marine scientist and a science educator for 50 years. And as you have shown, effective communication, education is theater, it's show business. And the last 20 years, I've worked on cruise ships all over the world as a naturalist, every summer, every week in Alaska, but also a couple dozen times in Antarctica, New Zealand, Australia, Norway, and definitely the glaciers are going away. We're seeing not only the climate, but the movement of animals and all of that. And one of the issues, I think, with the ocean temperature data that we had before was when you mentioned taking data from ships. They weren't taking samples from the ocean. They were taking samples from the water intake for their cooling for their engines. Well, by the time they measured the temperature, it had already gone through a bunch of piping and whatnot. So it was artificially elevated. So when we started taking actual ocean temperature, it's like, oh, it's dropped. And so that was part of the adjustment. And as I keep discovering and try to tell people, one of the questions I ask is, how does it feel to be wrong? How does it feel to be wrong? And people say, well, I'm embarrassed. I feel ashamed. I say, no. That's how you feel when you discover that you were wrong. When you are wrong, it feels exactly like when you're right, because you don't know that you're wrong. And so you feel very like, I know my stuff. And then you find out, and then all those other feelings come along. But part of the problem when you're dealing with people who think they know, is they feel perfectly justified. They feel exactly like when you're right, except that you're wrong. And that's a big hurdle. That's a big jump to go over. And as we keep discovering, it's much easier to fool people than to convince them that they have been fooled. And that's a huge mountain we have to climb. So thank you for what you're doing, and definitely show business and theater. We need that. Thank you.
Yeah, well, thank you for that story. It's a good one too, and I really like your point about how it feels when you find out you're wrong. I think part of what we need to figure out how to do as a community is to give those people the people we're trying to convince about climate change, give them permission to be embarrassed a little bit and to feel like it's okay that they were wrong, right? Instead of punishing them for it.
Give them room to maneuver.
Mm-hmm,
One of the
exactly.
things that, we all thought that at one time, but now we've discovered with more information, better data, give them room to say, yeah, well, okay, yeah, we all thought that once, but here's the change.
Right. I think that's a great point.
All right. Well, thanks again so much, Josh, for joining us today. Can we do one last round?
All right. Thank you, everybody. Thank you very much.
Yeah, if you had a pizza on a plate, if you could help us out by trying to keep the space clean, that would be super helpful. And have a great rest of your day. All right. Thanks again, Josh. I really appreciate that.